Okay, today we're here to talk about Robert Goddard. Goddard is known as the father of modern rocketry. And the reason he's known as the father of modern rocketry is because the work that he did with liquid-fueled rockets. We've had rockets for hundreds and hundreds of years. The Chinese have been using them forever, but they're all solid rockets. And even in the late 1800s, people talked about, hey, what if we could get up into space? What would it take? And they had all these calculations they made and everything. And what they figured out, if it ever was going to happen by the 1900s, is saying we really need some kind of what's called a liquid-fueled rocket. Because if this is a solid rocket, you put all kinds of like gunpowder in here. You light one in, and it burns, and sometimes it's pretty an uncontrolled burn. It's kind of hard to control, and once it starts, you can't stop it. But with a liquid-fueled rocket, you could shut it on, turn it off, and so on. And people have been trying to make it for a very, very long time. Well, Goddard was the first one to actually make a working liquid-fueled rocket. So today I'm just going to use a little Roncinol for my liquid fuel, and I'm just using the air we have already inside the bottle. So here is Robert Goddard's first attempt at a liquid fueled rocket, about 1926. Shaking around, mix. It's not the liquid that's actually going to burn here, it's the vapor. So I'm trying to get it all up in a vapor and everything. All right. First attempt, 1926 liquid fueled rocket. Well, his rocket actually worked better. It traveled somewhere. It didn't go very high. It did not go very high at all, but it came down and burned up somebody's pasture, and they spent some time afterwards putting the fire out in the pasture. But it was more successful than this thing. The idea was that there's no momentum to begin with. We've talked about the law of conservation momentum by about the right distance right here.
Yeah, perfect.
So here's the mass of the rocket and how fast it's going, mass of the gases on the inside and how fast those gases are going. Well, of course, they don't have any momentum to begin. They're both zero. So we're trying to look at what happens afterwards. Well, it turns out there's enough friction on that table that the gases did not come out very good. So what happens is the momentum of the gases going in one direction happened to be the same as the momentum of the rocket going the other direction, which it turned out to be seemingly zero because we actually had an external force of friction was great enough, didn't go anywhere. So this would be the mass, the momentum of the gases coming out. They had some momentum. A few gases came out very slowly. I know it wasn't fast because I could see a flame going straight up instead of backwards on the thing. So we didn't get much of a reaction, not big enough to overcome the external force of friction between the rocket and the table. So that's not impressive. So Goddard's first attempt wasn't super impressive either, though. So I don't feel terrible about it. But so what he did is he tried to figure out, so to get a better reaction out of this rocket, to make this mass of the rocket go faster, I need something to change here. You only have so much gases that you can have. The more mass you get coming out, the better. But also the faster. The faster those gases could come out in one direction, that's the greater the reaction you have the other way. So he started looking at, well, what can I do to make those gases come out even faster? And so something that he did is he's looked at how do you change the velocity of the gases coming out. So he put a little, well, he didn't necessarily, I'm putting a restriction on the end to simulate kind of some of the studies that he did of how to make those gases come out a little bit faster. Rocket test number 2. Little better. A little bit. It went 3 meters in less than a second. Okay? Sometimes that thing moves so fast I have a hard time timing it. So what I did is, to make it more of a working rocket, Peyton says she'd really like Anna to go up into space someday. So we made a new space contraption that's going to take off maybe and try to deliver Anna up into space here. Now, the mass of this is about 6.5 to 7 times the mass of original bottle. So if we have the same setup, 7 times the mass, what does that mean about the velocity? Think about it for a moment. So we're going to use the restricted end because we did a much better reaction than the first one. Maybe it wasn't super impressive, but it was still much better than that first reaction he had. Okay. So if this is 7 times the mass of the other rocket, what does that mean about the speed of it? Okay. So once again, I'm just trying to get the liquid mixed up into the air. It's the vapors that burn in the air, not the liquid fuel actually. It's the liquid fuel turning into a vapor that actually burns. Okay. So being 7 times the mass, I would expect it's going to slow down by maybe a 1/7 if everything works right, and I might actually be able to get a time on this and how fast it actually goes. Okay, so we have some data. So I stopped it over 1 meter, that's 0.74 seconds because it was spinning. I could have gone a little longer, did a little flip. So here's where we ended up. I stopped the time after 1 meter, and the time was 0.74 seconds. So 1 divided by 3/4 basically is 4/3. So that is 4/3 is 1.3 seconds. So it's 1.3 meters per second. So 1.3 meters per second times 139. The reason this is 139 is this is the mass of the gas. I calculated that at most that the mass of all the gas left, and it doesn't. If all the gas left, that would be 2.5 grams of air that's inside of that 2-liter bottle. And Anna, with the whole contraption, is 347 grams. That means that whole contraption is 130 times more massive than the gas is coming out. So that means the gases are coming out at 39 times the velocity of 1.3 meters per second. So 139 times 1.3, 181 meters per second. Okay, so that's almost 400 miles per hour that the gases were coming out. So that's not bad, not bad. But the idea what Goddard did is he found out by making the gases come out faster, you might have a much greater reaction out of the thing. So greater the action of the gases coming out, the greater the reaction of the rocket moving. So once again, this is all Newton's law stuff here, this law of conservation of momentum. End.